जाइनी। Hello. Yesterday we started discussing negative refractive index, and we saw classification of electromagnetic materials. So let me start from where we left. We divided the epsilon r mu r plane into four quadrants, each quadrant representing a mode of propagation. So if we are in the first quadrant, mu r and epsilon r both are positive, we said that the material supports propagating mode. If it is either in the second quadrant or the fourth quadrant, then either of them is negative, not both. If either of them is negative, we say the material which belong to these quadrants are supporting evanescent modes, and if it is the material falls under the third quadrant where both are negative, we say that it is again supporting propagation mode. So this is how we classified yesterday. These materials are called double negative material if they are in the third quadrant. Next. And there are synonyms for these materials. Uh, First is it is called double negative material. The reason is both the epsilon r is negative, mu r is negative. Since both are negative, so it is called double negative material. Then it is also called left-handed material or LH material. The reason is the propagation follows the left-handed rule, not the right-handed rule. The E field, H field, and the propagation vector k, they form a left-handed coordinate system. Therefore, it is called left-handed material. How they form a left-handed coordinate system, that we will see later. Then these are also called negative refractive index material. We have seen that if mu and epsilon both are negative, then the refractive index is negative because n is equal to C by Vp. From that we got n, and C by Vp. From that we get Vp being negative, so we got it to be a negative refractive index material. Finally, these are also called metamaterials. Metamaterial means the materials which do not occur in nature. These are engineered materials. So these are also called engineered materials. In this matter, because these are engineered materials, they are called metamaterials. They do not exist in nature. Now, let us see a short historical background of these materials. This was first time came into existence. For the first time, people saw that negative index is possible in a book called An Introduction to Theory of Optics by Schuster. This was published in London in 1904. So this is the first time when the negative refractive index was considered in an optical book, in a book on optics. Then, in same year, Lamb also discussed the effect of negative refraction. Pocklington in 1905 discussed about negative refraction. Maluginates in 1951, Sivukin in 1957, and Jengler in 1980. All these people have discussed about negative refractive index in optics. Next. Finally, in between these, Sivukin and Jengler, Viktor Veslegov from Russia, a Russian scientist, in 1967, he discussed the electrodynamics of a substance with simultaneous negative values of permittivity and permeability. So the others were discussing negative refractive index, whereas Vasilego discussed about negative permittivity and permeability, what will happen if both are negative. We'll discuss that later. Uh, then this type of Vasilego discussed it theoretically as a theoretical physicist in that time. Then Pendry, Sir Pendry in UK, he discussed how to realize a material which will give both epsilon negative and mu negative. That he designed and realized practically in 2000. So from 1967 to 2000, there was a null period. After 2000, people started working on this because it was possible to design a material with both negative epsilon and a negative. This is a short background, historical background. Now let us see the definition of double negative material and an effect of double negative material. By definition, the double negative material or left-handed material, these are composite materials, engineered materials, which exhibit effective electrical permittivity and effective magnetic permeability as negative quantities over a common frequency band. So these materials are designed in such a manner that over a frequency band, fixed frequency band or a common frequency band, epsilon will be negative and mu will be negative. What does this mean? This means that epsilon is varying with frequency or epsilon is dispersive. Mu is varying with frequency, mu is dispersive. Both of them can be positive or negative over certain frequencies, but there is a common frequency band over which both of them are negative. Beyond this frequency band, they can be positive or one can be positive, other can be negative. So all these materials are called left-handed materials or metamaterials or DNG materials. Now, if this happens, if both mu and epsilon are negative, how it is going to affect the electrodynamics? Because of this property, let us try to see that. So now what we will do is we will consider plain monochromatic electromagnetic wave. So since we are going to consider plain monochromatic electromagnetic wave, then in Maxwell's equation there will be one condition that we can always apply, that the del operator can be equivalent to minus I into k. This we can easily verify if we use the variation of the field as e to the power minus jkr, the variation in position. So spatial variation, if we consider it to be e to the power minus rjkr or ikr, then we can find out what is delta. Delta will be equivalent to minus ik. So we can always replace delta with minus ik in the Maxwell's equation. Let us look at the first Curl equation of Maxwell. Curl of E. Now curl of E is delta cross E. Delta is minus Ik. So we can write that as minus Ik cross E. Now curl of E is, we know, minus j omega mu h. Since mu is negative, so minus j omega negative mu into h, so negative into negative minus into minus, that becomes plus. So curl of E is equal to plus I omega mu h. Similarly, curl of h will be minus Ik cross h, which will be equal to I omega epsilon E, but epsilon is negative, so we have a negative sign. So now you can note the change in signs. In the Maxwell's equation, the signs change. That much you can notice for monochromatic wave when we have left-handed material. Now, using the Maxwell's equation, we can always derive the wave equation and the Poynting vector. Today, we will not derive these equations, but we will do the or we will get into the background of deriving these equations. Now, let us follow standard procedures to get the wave equation. Now, what is the standard procedure? Take the curl equation. So curl E, which is minus ik cross E, which is equal to plus I omega mu h. This we have seen. And take this. Then next. Curl H, this also we have seen is equal to minus ik cross H. This is equal to minus I omega epsilon E. Now, multiply minus ik on both sides of the first equation. So, the first equation now becomes minus ik cross E is equal to plus j omega mu into minus ik cross H. Now, plus j omega mu into minus ik cross H. Minus ik cross H from the second equation is minus I omega epsilon E. So for minus ik cross H, we put minus I omega epsilon E. Now, simplify this equation. If we simplify this equation, this gives us on the right hand side, let's take the right hand side term. The right hand side term is I omega mu into minus I omega epsilon. So plus I into minus I, that is 1. Omega into omega is omega square. Let me not take omega square. So that is omega mu into omega epsilon into E. So from that we can say omega epsilon into E is equal to the left hand side divided by omega. So left hand side is I k across ik. So from that I will take a minus I into minus I, divide that by omega mu. So minus I into minus I by omega mu into k cross E. Minus I into minus I is equal to minus 1. So minus 1 by omega mu. So this we can write as k cross minus 1 by omega mu into k cross E. So let us stop here in at this point today. From this point onward, with this equation, we will derive the wave equation in our next discussion. Thank you. Don't miss the next discussion. And if you have not seen the first discussion, please see the first discussion also, which is available in my website. This is not Guru